Hello everyone. So today's topic is image restoration in digital image processing. Till now we have studied the image enhancement techniques. We have studied a different spatial domain and frequency domain image enhancement techniques in digital image processing. So in many cases you may experience a noise in the input image. In order to remove the noise, you can go for image enhancement or image restoration. So the basic difference between image enhancement and image restoration is in image enhancement the degradation is not known, but in image restoration you can add a noise like a Gaussian noise, a uniform noise, or a Rayleigh noise. Different types of noise you can add to the input signal in order to remove the noise. So we have studied in image enhancement that if I want to remove the salt and pepper noise, I will go for the low pass median filtering where I arrange all the coefficients from the mask in a ascending order, and I replace the target pixel with a median value of all the pixel values. That was one of the image enhancement type. Now, the basic difference means you will get the desired output, but in image restoration, the output should be equivalent to the original one. You need to reconstruct the image after, means how can you actually experience the noise in the image? So if you are if, uh, if you are acquire the image with the camera sensors while image acquisition, you can face there is extra disturbances of noise within the image. During the transmission you may feel the noise has been added in the image. There are different processes while taking the image, while transmitting, while showing. You can have the different types of noise in the input image. So the basic model for the image restoration is, if you have a degraded image, that is g of xy, if f of xy is the input image, you will multiply it with a degradation function h. If f of xy is the input image, then you will add a degradation function, you will multiply your input image with a degradation function h. Normally we represent this degradation function by h of xy, and then you will add a noise to it. Now the noise can be anything. Noise can be Gaussian noise, uniform noise, Rayleigh noise, gamma noise. The noise can be anything. And then you will have the degraded input image, that is g of xy. So g of xy will be equivalent to the f of xy multiplied by h of xy plus the extra added noise, that is neta xy. That will be the g of xy. And then you need to do the restoration. First you will degrade the image, that is the first process is degradation in image restoration. So prior to your restoration you need to degrade the image using a degradation function and a noise, and then you will go for a restoration function using restoration filters, and you will get the restored image. Okay, now this is degradation, where the degradation function is denoted by h, additive noise neta xy. Yes, if you're considering g of xy in a spatial domain, so I can represent g of xy will be equivalent to h of xy multiplied by f of xy, that is your input function f of xy, that is input image or input pixel. F of xy should be multiplied by our degradation function or degradation pixel h of xy, plus you will add some noise, that is neta xy. So the Fourier transform of this g of xy I can write using convolution theory. I can write g of uv, that is the Fourier transform of g of xy, that is g of uv, is equivalent to h of xy का Fourier transform h of uv, and this multiplication, it is in a Fourier transform as f of uv plus n will be represented capital N of uv. So this is nothing but the Fourier transform of your spatial domain. So you have transformed your spatial domain input image into a frequency domain. Okay. How can you actually add a noise? Uh, Now in image restoration, we basically add a noise in a degradation process, and then we restore the image into original position. You may experience a source of a noise while viewing the image. You can have the noise while performing image acquisition. That is, I am actually capturing the image of an object through a camera sensor. While acquisition of an image, I can experience the noise. While digitization process, that is sampling and quantization, uh, I can experience the unwanted noise to be occurred in that input image. Or while transmission for a long distance, or a transmission from one end to another end, from source to destination, I can have the additive noise in my input image. So source can be anything. So source can be right from the acquisition up to transmission and up to display of an image. So there are white noise. Now white noise is nothing but it has the uniform Fourier spectrum. Now, what is a white noise? If I will go for the next presentation, I will show you that. This is nothing but a uniform noise, or you can say the white noise. It has a uniform, that is a uniform amplitude from A select B. Okay. So if you consider this degradation model, g of xy is equivalent to f of xy multiplied by h of xy plus nxy. So in multiple books, they are denoting the function by neta small n for a noise. So they can specify any of the word for this. Your basics should be clear for the degradation model. So from convolution theorem, we can actually convert this spatial domain into a frequency domain. That is, g of uv is equivalent to f of uv into h of uv plus n of uv. And to get f of uv, I will shift this n to this side, so g of uv minus n of uv, and this multiplication will be the division in other side. So I can actually have the f of uv if I have g of uv, n of uv, and h of uv. The difficulty that you can face is unknown n of uv and h of uv in the degradation model. So the noise can be originate from your image acquisition, digitization, and transmission. White noise, the noise whose Fourier spectrum is constant. Okay. Suppose this is a noisy image, the original image like this, the periodic noise. After each and period, the interval, you will feel there is a noise has been added to the input image. Okay. Additive noise means each pixel is added to the noise. Okay. And probability distribution. Now, what is the probability distribution? Probability distribution means we are considering the histogram of an input image. Suppose if you have the input image which is made up of the value 3, if the image contains the value or the value of a pixel 3 100 times, the histogram you will draw on your graph paper for 100 on a y-axis. That is the probability of occurrence for the value of 3 in the input image. So I can create a histogram for each and every pixel, for each and every probability of occurrence of a pixel, in order to get the histogram information. Then you have a salt and pepper noise. We have already studied in the image enhancement how we remove salt and pepper noise using low pass median filtering. So you can add this salt and pepper noise. Okay, so the function that is a px, the px, this is px actually. So px will be pa for x जिसका input का value equivalent to a है. Then another salt and pepper noise will be pv, another noise with another amplitude for if you have x is equivalent to b. So you have a certain value for that point a, b and all, and otherwise zero. So either you can have different types of amplitude value of a noise, and you can add directly, that is salt and pepper, either zero or any kind of value. Okay, so if you consider this range, if 0 से लेके इतना PA है, 0 से लेके इतना PB है, so the remaining will be 1 minus PA plus PB. Okay, this is nothing but a salt and pepper noise. This is the input image. I can add this noise to the input image like this. So I will be having a noisy image, that is salt and pepper noisy image. So PA for x is equal to A, PB for x is equal to B. That is the function for salt and pepper noise. Okay. Uniform noise. We have already studied in a thresholding image enhancement that if you have the value like this L minus 1. Now, actually it is nothing but the formula that is 1 upon B minus A. That is a slope formula. So if you consider this function, this function on a y-axis can be represented by 1 upon B minus A. Okay, so the function for the uniform noise will be P of x is equivalent to 1 upon BA if the value is in between A and B. That is, x will be greater than A and less than or equal to greater than equal to A and less than equal to B. So for this region I will have the function 1 upon B minus A, otherwise it is 0 in either side of your this density power density function. And here we need to consider the mu is nothing but the average between A and B, the average value, that is mu here, average value A plus B by 2, and the variance, so deviation, and after deviation, after squaring the deviation you will get a variance. So variance will be B minus A square by 12. Now, how we calculate mu as a average, and how do we calculate the sigma square, that is another variance, is B minus A the whole bracket square divided by 12. So the explanation has been given here. Now I can derive the mu from the expected value of x or estimate value of x. Okay, so what is the estimate value? When you're doing an estimation or expectation from this, you need to consider the integral of the function. So you're considering from minus infinity to infinity, and the function of x is nothing but x into px into del x. Okay, that will be the x function, that is expected value of x function, x multiplied by this function into del x. Now we are calculating for this region, that is the region between A and B. So my limit will be from A से लेके B. So integration from A to B for the x. And what is the P of x? P of x, if you are in between A and B, 1 upon BA del x. This will be the constant one. I will remove out of your integral. Then now out of your integration you will have the constant as 1 upon b minus a, and then you will have the another limit that is from a select b. You need to verify x dx. Now what is this? The integration formula for x del x is nothing but x square by 2. So you will have 1 upon b minus a x square by 2. That is the differentiation. That is the function. X dx is nothing but x square by 2, and then you will go for limit a and b. So you will replace this a square by 2 minus b square by 2. So you will have like this, sorry, b square by 2 minus a square by 2. So you will replace this in x, in this x. So you will have b square by 2 minus a square by 2 is nothing but 1 by 2 common, b minus a square. So you will have a plus b, because what is the formula? B square minus a square. B square minus a square is a plus b and a minus b. Okay, so b minus a multiply by b plus a. So b minus a will be cancelled, and you will be left with a plus b by 2. So that will be the formula for your mu. Okay, now what is a mu here? Your mu is mean. Your mu is nothing but a mean. Sigma is standard deviation, and sigma square is a variance. Okay, now we have got the mu value, that is this a plus b by 2, that is a mean for this power density or power spectrum. This is nothing but the power spectrum of uniform noise. This is a power spectrum of uniform noise. This is a power spectrum of uniform noise. So I can add this noise to this image in order to get the noise, or you can say the degradation. It is nothing but you are adding a noise. Okay, and now how do we calculate the sigma then? Now sigma square, in order to get the sigma square, the formula is you need to calculate the expected value of difference between x minus ex ka whole bracket square. Now you know the formula for a minus b square. A minus b square, a square minus 2ab plus b square. So you will have expected value of x square minus 2 plus ex square. So ex square minus 2 ex plus ex square will be minus 2 ex square, plus ex square will be 1 ex square. So you will be left with ex square and whole bracket ex ka square. Okay, now you know the expected value of x already, you have calculated. So I will actually solve the problem for this. So you have expected value x is a plus b by 2. This is, we are considering now the square, so a plus b divided by 2 ka whole square. Okay, so I will replace this value in this, a plus b divided by 2 ka whole square, and I need to calculate this. Okay, so x square p of x del x minus a plus b divided by 2 ka square will be 1 upon b minus a, that is p of x or x square. And what is the formula for square? X cube divided by 3. Okay, and this function, so 1 upon b a, to be a px क्या है? Px is nothing but 1 upon ba, 1 upon b minus a. So ये यहाँ से कॉमन निकल जाएगा, 1 upon b minus a, and then you will be with only x square function with del x. And you know the formula for this x square del x is x cube divided by 3. Okay, you will keep it as it is. So you will have the constant 1 upon b minus a, 1 upon 3, that is x cube minus 3, sorry, x cube divided by 3 is this. Okay, then b cube minus b cube divided by 3 minus a cube divided by 3. Okay, same function as it is here. Okay, and when you solve, and you will get the function a minus b a minus b the whole bracket square divided by 12. So that will be the variance after solving the final equation for the variance. Okay, so the square of deviation a minus b cos a minus b is whole bracket square divided by 12. Okay, so that is why we have written that is mean is equivalent to a plus b by 2, and the variance is equivalent to b minus a squared divided by 12, and that is actually the uniform noise where you consider uh, mu value and sigma value and variance value. Okay, because normally this is a Gaussian noise. Okay, hmm. This is Gaussian noise, Rayleigh noise, gamma, exponential, uniform noise. Different types of noise you can add to the signal. Okay, uniform noise. Similarly, the Gaussian noise, in a Gaussian noise, the graph of a Gaussian noise will be looking like this. Means it represents some sines and cosines within it. So normally we represent our sines and cosine function by exponential, complex exponential. Okay, so the Gaussian noise function p of x will be 1 by under root of 2 pi sigma multiplied by exponential raised to minus x minus mu whole bracket square divided by 2 epsilon square, where mu is a mean, that is expected value of x, sigma square is a variance. So the Gaussian noise for the highest amplitude you will have 1 upon 2 pi epsilon. For the this level you will have 0.607 upon under root of 2 pi uh, sigma. Okay, so you have the level that is mu minus sigma. This is the middle value you will when you hit the topmost value of your Gaussian noise, you will be at mu, and the equivalent distance, you can say, from your center point will be mu minus sigma and mu plus sigma. Okay, in some book they have the 70% of its value will be in the range of mu minus sigma and mu plus sigma, and 95% of its value will be in the range of mu minus 2 sigma and mu plus 2 sigma. Is for the next 2 sigma you have added one more signal. Okay, this is a Gaussian noise, 1 upon 2 epsilon 1 upon 2 pi 1 upon under root of 2 pi sigma uh, multiplied by exponential minus x minus mu whole bracket square upon 2. You need to mug up this formula, okay, for a Gaussian noise. And then you have a Rayleigh noise. So in a Gaussian noise, only sines and cosines with the amplitude. Hmm. And in Rayleigh noise, there is no signal at all. If you start from 0, after A, you are starting your Rayleigh noise. So for this Rayleigh noise, you can have a function in uh, in two quantities like 0, and if you have something in a Rayleigh noise, then you will give the function like 2 upon b x minus b into exponential, as it is also made up of sum of the sine and cosine. So because what is e raised to j theta or theta, that is cos theta plus j sine theta for e raised to j theta. Means it is made up of cos and sine. Okay. So the Rayleigh noise is the function px. This is a noise function px. It will be for this curve from यहाँ से लेके यहाँ, and it has been derived by 2 by b x minus b x minus b, because you are not considering this distance, so you need to subtract x from entire x minus b. Okay, and then sorry, x minus a, not b, x minus a into exponential minus of x minus a square upon b. Okay, for x greater than or equal to a, for x greater than or equal to a, तभी जाके ये पूरा फॉर्म मिलने वाला है. Otherwise it will be 0. If x less than a, it will be 0. Here the mean is equal to a plus under root of pi b divided by 4, and variance is nothing but b 4 minus pi divided by 4. Now in examination they will not tell you to actually derive the expression for mu and variance for the Rayleigh noise and all. They will ask you what is the Rayleigh noise, and what will be the function of Rayleigh noise with a neat and labeled diagram. They may ask you. Okay, so this is a function for Rayleigh noise. The Rayleigh noise is looking like this, and your Gaussian noise like a symmetry. You have a symmetry, mu minus sigma, mu plus sigma, which may mu. That will be the symmetry. Yeah, no symmetry. Suddenly you will start your Rayleigh noise from A. After A, you will be getting the waveform from Rayleigh noise, and this, it is actual structure of your Rayleigh noise in the output. Okay. Then Erlang or gamma noise. So Erlang, most probably we use a gamma noise as a function for a noise. So gamma noise, p of x will be equivalent to a to the power b x to the power b minus a divided by b minus 1 factorial multiplied by exponential minus ax for x greater than or equal to 0. You need to start from directly after 0. 0 के बाद जो भी है वो पूरा नॉइज है. So if x का value greater than 0 है, you are in a noise. Okay, and the function for the noise is this. Here mu, that is a mean for this, or you can say mean is nothing but the average. The average value for this noise will be b by a. b by a, अगर वो x के less than x है, sorry, x is less than 0 है, then it will be 0. So it will be 0 for the negative values, 0. And variance square, that is variance sigma square, is given by b upon a square. So it is quite similar to your Rayleigh noise, but the basic difference is the Rayleigh noise starts from a and your gamma noise starts from 0. Okay, this is exponential noise. So exponential, from the graph only you can actually relate that graph as it is exponential. Okay. Okay, so the exponential noise p of x is nothing but a multiplied by e exponential, that is exponential. The power is minus ax for x greater than equal to 0 क्योंकि 0 के बाद ही चालू हो रहा है. When you hit the 0, after 0 you will be in a noise. So if you have the values greater than 0, you will be having a function a into exponential raised to minus ax, where mean mu is defined by 1 upon a, and your variance defined by 1 upon a square. So the formulas are very similar, simple for exponential noise and a gamma noise for mu and variance. For gamma b by a, mu b by a वहाँ पे 1 upon a है, and sigma square 1 b upon a square है, वहाँ पे 1 upon a square है for this exponential. As it is exponential, it should contain the exponential term. Okay. Hmm. So the estimation of noise parameter. So if you have some h of xy and noise neta xy, you can calculate. You can actually derive the expression for your restored value. So we have already studied that is mu, that is expected value of x, and h of xy. So h of xy is nothing but the degradation function. That is जब अपन expectation of x निकाल रहे थे, then we were considering p of x, that is noise function, and determine the probability distribution from the shape of h of xi. Estimate the parameters of probability distribution using mu and sigma square. Okay, so if you have a mu 0 and sigma 0, you can calculate the value for b and a. That is, you can get the value for sigma, or if you have mu 0 and sigma square. So you can have the b value that is in terms of this. Then for really you can calculate the value for a. Okay, and the remaining part we will actually cover in a next video. Till then, study this restoration model and all types of noise that we can add in order to restore the image. Okay, thank you.